Hello, Matthews Gatos here. I want to do section 7.2 with you, but before we do that, let's review 7.1. So I want to start by doing a diploma example here to review. So we have a town population increasing at a constant rate of 2.6% per year. So I have 100% or all of the previous amount plus an extra 2.6%. Now remember, bases are never listed as percentages, they will be as decimals, so that will be my base. This year on January 1st, the town's population was 16,000. That's my initial amount. The minimum number of complete years from January 1st that it will take for the town's population to exceed 20,000, that's my final amount, is, and then we want to solve from there. Okay, this increase is happening per year, so that tells me my period is 1. So let's put that all together in my form A times B to the T over P, which again is on your formula sheet. So 20,000 is the initial amount, 16,000, multiplied by my base, raised to the exponent of T over 1. So for this question here, I am going to use method number 1, which is y1, y2 intersect. So I'll put this into y1, this into y2, find out where they intersect. So to go into my calculator here, I have left side in y1, right side in y2, and I just need to adjust my windows. So x is a measure of time, so I just went 0 to 10 years up by 1, always starting with 0. Y is the population. So I went from 0 up to, now we want to get up to 25,000. I went just a little bit above that at 25,000, up by 1,000. And again, you can always adjust that if you need to. So there's my graph. I can clearly see the intersection point. So I just go second trace, option number 5, enter, enter, enter. And you can see I get 8.69. So again, the question comes, how should I round that? So we talked about that in the last lesson, but I'd like to show you again. Let's just look at our table. If I go into my table, let me start my table at 0 years. Okay, so if I look at, I want to know how do I round it. So it was 8.69. So it's either going to be 8 or 9. So we can look at these two here. If it was 8 years, you can see here the population, 19,647. 9 years, it's 20,158. So I want to exceed 20,000. So I can't say 8 because it hasn't reached it yet. I have to round that to 9. So it's over 20,000, but that would be my answer, is 9 years. So the number of complete years, 9 years. Okay, let's try another one. Joe invested $4,500 at a fixed annual interest rate compounded annually. If at the end of 12 years the investment has doubled in value, to the nearest 100%, Joe's investment plays blank percent per year compounded annually. Okay, so again, our formula, y equals A times B to the T over P. So let's go back and read the different parts here. Okay, so I've invested $4,500. That's my initial amount. I want my investment to double. So that means my end amount will be 9,000. It is compounded annually, which means I get paid interest one time a year. I am looking at the end of 12 years, so that's my time. And in this one, we're going to be solving for the base. So end value equals initial value times by the base to the exponent T over P. Okay, so I'm going to divide both sides by 4,500. And I'm going to get 2 because 9,000 is double. B to the 12 divided by 1 is just 12. So I have B to the exponent of 12, and I want to solve for that. So to do that, I'm going to take the 12th root. So take the 12th root of 2. I just want to make sure you guys know how to do the 12th root on your calculator. So if we go in here, and I want to do the 12th root, I'm going to enter in 12 and then I'm going to go math, and I'm going to go down to option number 5, which is x root. So that's any number first, but you have to put the number first. So it's the xth root, but we already did 12. So I'll do option 5 and see it does the 12th root. And I'm doing the 12th root of 2. So there's what my base is. Remember, this is a percentage, so I'll times it by 100. So that's the percentage. So you can see it's over 100% because it's growing. So it's all of the original amount plus the extra. To figure out what the extra is, I just subtract 100, and that would be the extra. So it would be growing at a rate of, they want it to the nearest hundredth, that would be 5.95. So the base is equal to 5.95. Okay, in this lesson here, we're going to look at 7.2, which is transformations of exponential functions. So back to chapter 1, we're just doing it now with an exponential function. So what we're going to be looking at is transforming an exponential function to this form here. Now, you'll notice that in the last lesson, I used a small b for the base. I said y equals a times b to the x. Because we're talking about transformations and I don't want you to get your b's confused, I'm going to use a big letter B for the base, and then that small letter b here, so you don't get it confused, is the chapter 1b, which is your horizontal stretch or reflection. Okay, so just so we don't confuse those, big B for the base, little b for the transformation. So here I have, and this is the same chart we do for every single chapter, just a little review of chapter 1. Okay, what I want you to remember again is the horizontal factors lie. So horizontal stretch lies and horizontal translation lies. Be aware of that. Okay, so just to make sure we're all okay on this, here in general is the function notation, which is on your formula sheet. A f of b x minus h plus k. Remember, on the outside, the a and the k value, those are your vertical values which affect y. On the inside, the b and the h, those are the ones that affect your x values. And again, remember that anything horizontal lies like Pinocchio. Anything that is vertical is straight up honest, exactly as it appears. Okay, so a vertical stretch, anything vertical, affects the y coordinate, just like a vertical translation affects the y coordinate. Horizontal ones on the inside affect the x coordinate. So horizontal stretch affects x, and a horizontal translation also affects x. Okay, let's apply this to some functions. So we have the function y equals 4 to the x. We are going to vertically stretch it. Let's just go through this a piece at a time. Vertically stretched by a factor of 1/3. Vertical is straight up honest, so I know that a equals 1/3. It is horizontally stretched by a factor of 4. Remember, horizontal lies like Pinocchio, so it is not 4, it is 1/4. Reflected over both axes, so that means a is negative and b is also negative. It is translated 5 units left, h is -5, 7 units up, k is +7. So I want to write the new function g of x. So g of x is going to equal to a big B for the base, which is 4, little b for the transformation, x minus h, so minus a -5 is actually a +5, plus my k value. So that would be my equation. Let's write the transformation in mapping notation. Mapping notation is literally what I'm doing point to point. So I'm horizontally stretching it by 4 and reflecting it, -4x, and then I'm moving it left 5 units. Y values. I'm vertically stretching it by 1/3 and I'm reflecting it, so -1/3, and then I'm moving it 7 units up. So that's my mapping notation. So if I want to know what happens to this point 2 and 16, So I'm going to substitute the 2 in for the x, and I'll substitute the 16 in for the y. So substituting in the 2, I'm going to have negative 4 times 2 minus 5. So that works out to be negative 13. Negative 1/3, substitute in your y value, plus 7. Add those together and I get 5/3. So the transform point 216 becomes the point negative 13 and 5/3. Last question, what is the equation of the horizontal asymptote? So horizontal asymptote, that y equals equation, is only affected by a vertical translation. So if you think about my base function that we learned in 7.1, my base function had a horizontal asymptote of 0, but I've moved this new function up 7 units. So the horizontal asymptote will also move up 7 units to be y equals 7. Okay, let's try another one. So I have a base function, 2 to the exponent of x, and this time I'm given the transformed function, and I want to describe the transformations. So my transformed function, y equals g of x negative 1/2 times base 2. So see, the base stays the same, okay? And it's 2 to the x minus 3 minus 5. So let's just do this in pieces, okay? Let's look at the negative 1/2 in the front here. So the negative 1/2, that's my a value. So that means that I'm stretching it vertically by a factor of 1/2, and I'm also reflecting it. So all my y values will be negative 1/2 y. So let's look at the negative tells me that I am having a vertical stretch. So I know that I have a vertical stretch. A value is 1/2 by a factor of 1/2 about the x-axis. The negative tells me that I have a reflection. So notice I don't say that my stretch is negative 1/2, it's just 1/2. So the negative there tells me I have a vertical reflection, and that will be in the x-axis. Let's keep with vertical. On the outside, I have a -5. So that means that I'm taking all my points and moving them 5 units down. So I have a vertical translation of 5 units, and that will go down. Okay, let's now look at our horizontals. Okay, so B is the base. Let's look at this 2 here. So this 2 here tells me that I am doing a horizontal stretch by a factor of 1/2. So I have a horizontal stretch, because remember horizontal lies, by a factor of 1/2 about the y-axis. So all my x values are 1/2. Okay, and then I have this -3. So because horizontal lies, that's not left 3, that's actually 3 right. So I have a horizontal translation of 3 units to the right. So I would just add on 3 to all of my x values. So there I have the description and also the mapping notation. So I want to delve into this function a little bit in more detail. So I want to compare the base function and the transformed function side by side and talk about the comparisons between domain, range, asymptotes, x and y intercepts. So for all exponential functions, there's no restriction on x. And remember, when I'm talking about restrictions, I'm talking, am I dividing by 0? Am I square rooting a negative? Or in chapter 8, we'll look at, am I logging a negative? But for right now, the domain for both of these is going to be the set of all x such that x is an element of the reals. The range has to do with y. What am I doing with y? Well, I know just looking at my base function here. Looking at my base function, I have a base of 2, which means I'm an increasing graph, and it's going to be everything above 0. So the range is the set of all y such that y is greater than 0 and still an element of the reals. Now, let's talk about our base function. We'll start with our base function first. So base function here has an asymptote, a horizontal asymptote at y equal 0, which means there's no x-intercepts. The y-intercept is found by letting x be 0. So if I plugged in 2 to the 0 into my calculator or did it myself, I would get a y-intercept value at 1. So my my y-intercept is at 0 and 1. Now, let's compare that to the other graph. Okay, so this other function here, the whole graph has been reflected, so it's going from an increasing graph to a decreasing graph, and then it's going to move down 5 units. So it's going from increasing, I'm reflecting it, so it's going to go decreasing, and then it's going to go down 5 units. So that means that instead of being greater than 0, I'm less than 0 with the reflection, but that 0, the horizontal asymptote, has been moved down 5 units. So it's going to be less than -5, but still an element of the reals. And again, the reason that happens is I have a vertical reflection and I'm translating it down 5 units. So I have a horizontal asymptote at -5. Now, because I have a graph that's decreasing and it's gone further away from the x-axis, down -5, this graph also has no x-intercept. To figure out the y-intercept, all I do is replace x for 0 in the original equation. So right there, I can just replace that with 0, and I can work out what that is, or I can just simply substitute it into my calculator and figure out what my y-intercept is. So doing that on my calculator, I can get a point that is just below the horizontal asymptote. So there's my y-intercept. I would write that as 0 and -5.008. Okay, I want to put this all together and look at the graph. So let's look at the graph. So here I have the graph of 2 to the exponent of x, my nice base function. Now, this function here, we're going to put it together. We're going to have a vertical reflection. It's going to be decreasing. Horizontal asymptote at -5, y-intercept at -5.008. So looking at this graph here, that's what it looks like. So you can see this graph here, reflected. I have a horizontal asymptote at y equals to -5. So I can just draw that on there. And the y-intercept just a smidge below that. So that's what the graph would look like. Okay, in my last example, let's go through some more transformations. This time, instead of with the function given to us, we're going to look at the function in transformed notation. So instead of a half to the x, it's now in function notation. And then we're going to write the equation down here in terms of x. Okay, so we have this base function, a half to the x, and we're transforming it as follows. So again, let's focus on our outside pieces. Our outside pieces are the y values. So the 2 there tells me that I have a vertical stretch. So I have a vertical stretch by a factor of 2 about the x-axis. So let's start to build our function. Instead of function notation, I'm talking about what am I doing to this 1/2 to the exponent of x. And right now on the outside, I'm stretching it by a factor of 2, and I'm moving it up 3 units. So that will be the vertical translation of 3 units up. Okay, let's move to our horizontal. Horizontal is on the inside pieces here. Okay, so let's talk about the negative first. So the negative here tells me that I have a horizontal reflection in the y-axis. Let's talk about the quarter, because remember, horizontal lies. So it's not a horizontal stretch by a quarter, but in fact a horizontal stretch by a factor of 4. And that's about the y-axis. So in my exponents, I have a reflection and a horizontal stretch by a factor of 1/4. And then the last piece I have here, this -8. -8 looks like it's going to the left, but horizontal lies. So I know I have a horizontal translation of 8 units to the right. And that will just be x minus 8. So there is my function g of x, and this is in terms of x. So whenever I ask you for a formula or an equation in terms of x, I want you to go back to the base function. This here is function notation, which is in terms of f of x. Okay, let's summarize this lesson. So to summarize, A value, again, has to deal with vertical stretches and reflections. Remember that anything vertical is straight up. B values are the horizontal stretch and reflection. Remember that horizontal lies. Okay, I use a big B for the base and a little b for the horizontal stretch and reflection, the horizontal parameter. Your H value is your horizontal translation, remembering again horizontal lies. K value is your vertical translation. And mapping notation, of course, is literally what is happening point to point. So today's joke, it just always makes me crack up, imagining this T-Rex with these tiny little arms trying to graph an exponential function, which you and I would have no problem going up. But because his poor little short arms, he gets up to that point and then he can't quite make it and it tapers off and he has to drop his marker. I think that's so funny. So what I want you guys to do is do my practice questions, numbers 1 through 8, and then you can go on to do the textbook questions that are listed there.